So let's turn our attention now to the process of system identification as part of modeling of systems. You will recall that in the previous few lectures, we have been explaining that there are generally three types of models that you might get out of your process or plant. These are differential equation models, transfer function models, or state variable models. Now, we said, generally speaking, in order to derive such a model or any of the models for thermal system, electrical system, mechanical or fluid flow system, you would rely on two common techniques. The first technique is to use the physics of the model or natural science, whatever, if it's the chemistry, whatever relevant science that explains how fundamentally the system operates. The second alternative to this is called system identification. So the lecture today is about system identification. So we'll go through the introduction, we'll explain the system identification procedure and consider a small example for illustration. So sometimes we have explained that it may not be so easy to get an ordinary differential equation or a transfer function or state-space model of a system because of many different reasons. One could be that the physics is too complex. One does not understand them, or there are too many interactions because the system or the plant is too big to the point that it's going to be overly complex to try and model from the basic sciences. Sometimes it's that the process dynamics are not well understood as the process or some of the equipment in the process start to age, the dynamics are changing. There's some differences between how the system had to operate when it was brand new, and as compared to now that it has got some wear and tear. Or sometimes it could be that the modeling process could take too long. So you need system identification in this case. So system identification, what it does is to use experimental data to derive your model. So in this case, remember our view of a process is that the process it's made up of this black box which you don't know, but you interact with it by giving it inputs and observing its outputs. So the model, whatever the model is, whether it's an ordinary differential equation, state variable, transfer function model, you would want to understand what the value of the parameters is, that is the parameters that make up the model, as well as what could be the states or how many states could the process have. So there could be 4 different variations of the system identification process based if the plant is linear or if it's non-linear. You could also derive a plant model which is parametric or other models which are non-parametric. For the purpose of this course, we will focus on parametric linear types of systems. So the idea of a parametric modeling process in this case is we have a model G. So the modeling function or differential equation, in this case, let's say it's G, which we don't know. Because we don't know the model, the way we do it with parametric modeling processes, we guess a model structure. We get a model, say M of theta. We guess that the system could possibly have a structure M and parameters theta. And now the process, our job becomes now to check if this guess of ours is successful, and secondly to find out what the value of the parameters is. So the process which we embark on can be summarized as thus. The first step is to assume a given model structure, M of theta, and then we conduct then an experiment to obtain input-output data. So we give it a certain different types of inputs and we observe the output, and then based on that we try and match. We try and find the parameters of the model structure that we have guessed, the parameter values which when we feed them into the data, they give us the lowest amount of error. So it is an optimization function where we we compute the cost function J of theta, which is basically we try and reduce the amount of error that we get in the model. So we try and find the optimal parameters which give us the smallest amount of error. Now, if we test if the error is small enough, if the error is small enough, then we know that we have found the best model. We stop. If the error is not small enough, then it means we need to change. We either go back to the step where we conduct a different experiment, or we can go back to a step where we guess a different type of model. So now let us consider, for instance, let's say we have a model for the following system, and our guess is that the system would have this structure of a model. So we guess the structure. Now what it means therefore is that we will gather experimental data based on that. So we will give it multiple inputs. We'll give it input u1, and then we give us output y1. We give it input u2, gives us y2. We give it u3, gives us y3, and so on and so forth up until the nth input. So let's say n is 100. We give it the 100th input, give us the 100th output. Now based on that, we can reconstruct therefore an equation trying to relate these unknown parameters. Remember, theta 0 and theta 1 are unknown. We can reconstruct a set of equations that y1 would definitely be equal to theta 1 times u1 plus, theta 0 times u1 plus theta 1 plus another error, a possible error that may have occurred in our experimentation. Y2 will be equal to theta 0 times u2 plus theta 1 plus error 2, and so on and so forth up to the nth equation. So we observe that now we have a system of n equations and two unknowns which we don't know. So we have two parameters that we don't know. Just turning our attentions to the error, first of all, we will notice that the model can never be accurate because there will be some modeling inaccuracies. So the error in this case would account for those modeling inaccuracies. The model in actual fact in reality might be, the system in actual fact might be nonlinear, while the model that we are guessing is a linear approximation of it. So because of nonlinearities, we would also tend to get some errors. Sometimes there might be some time variation in the system. So the system might not necessarily be time invariant. It might change whether you're making an experiment in the morning or in the afternoon. There might be those differences. And then also you might have some measurement errors. So there might be some noise in your measuring instruments. So you are bound to get some form of error as you're modeling your process. So our understanding is that the equation won't fit perfectly. The equations would fit even if we knew what the parameters were, but they will have some small amount of error. So our problem then of system education becomes reduced to guessing the values of theta 0 and theta 1, given n equations, which might be a lot, let's say 100 equations. What would be the value of theta 0 and theta 1 that fits this data? Now, how do we then solve this? So in order for us to solve these equations, we can place them in matrix format. So in fact, we see that these equations would simply fit in matrix format the following. It would be like assigning a column vector y1, y2, y3 up to yn is equal to the multiplication of two vectors here plus some error which we don't know. So in this case, then we can also show that in fact this middle portion is the same as multiplying a matrix with the inputs here and all ones here, and multiplying it with the unknown values of the parameter theta 0 and theta 1. Remember, in this equation, what we simply have is, one, we have this information of u1s, we have this information of y1s. but we don't know what theta is. In fact, the error, we don't know also what the errors are as they occur. So we can forget about that term. So in actual fact here, we have an equation where we know this bit, we also know this part, but we don't know the theta. The theta in this case here, theta, the big theta is simply a vector containing theta 0 and theta 1. And this becomes the big Y, which is the vector Y, and then that becomes the vector, sorry, the matrix phi. Now, it can be shown using a small, using simple mathematics that, in fact, the optimal value of theta, or the best value of theta that fits this equation that we have here, the best value of theta that fits this equation can be written as phi transpose times phi, all of this inverse times phi transpose times y. So in this equation, we can reconstruct using what we know. Remember, we said we know the values in phi, we know the values in big Y. So in actual fact, this gives us hope, because what it means is that we can use the values of phi plus the values of y to calculate the optimal value of theta. Now, in fact, this has this value here, theta transpose, phi transpose times phi inverse times phi transpose. This value has a very common or famous name, which is called a Moore-Penrose pseudo-inverse. So it means, therefore, in order for one to calculate the optimal parameters in system identification for a linear system, it simply means that the problem is reduced to simply calculating the Moore-Penrose pseudo-inverse from the data, and taking that Moore-Penrose pseudo-inverse and multiplying it by the output data. That should give you your optimal parameter, theta star. So you will see, in fact, in the experimentation that you will do in the lab, that the system identification process is simply reduced to calculating these two things and organizing your data into vectors. So now, in our process, as initially explained, you have assumed a model, and then you have conducted an experiment to give you this data. After doing that, the next step is now to construct the phi, because you already have the y. And then after doing that, you will simply calculate the theta after creating this Moore-Penrose inverse. And from there, you can calculate now what the error of the model is, the error of that the model gives you. So based on that, you will know if this error is small enough or not. And you can use that judgment to then iterate backwards to step 1 or to step 2. So in this case, let's make a small example of the computation and how it can be done. Consider system engineer has suggested that the model may be of the following structure, and you as a technician have to carry out this system identification procedure. Now, in that case, let's say, for example, you have taken, you have given your system the following inputs: U1, U2, U3, U4, U5, and then you get these following outputs: 1.32, 1.70, 2.07, 1.56, and 3.3. Now, it therefore means that, in fact, you have this system of equation, which is 5 simultaneous equations. And the task is to use these 5 simultaneous equations to solve the best values of theta 0 and theta 1. So even if you knew from your mathematics as an avid mathematician, you knew how to solve simultaneous equations, you will notice that because this system of equations has some errors, not the parameters that you may find taking any two and solving the simultaneous equation will not necessarily fit into the third one. So in actual fact, this is an optimization problem when you are trying to find the best values of theta 0 and theta 1 that will fit all equations whilst giving the smallest amount of error for all equations. So you can't simply do it as a simultaneous equation, even if you were able to solve 5 simultaneous equations. And sometimes, of course, you can take thousands of real-world experiments and this becomes thousands of equations that you may need to solve. And so finding these real values or the optimal values of the parameters is not a trivial problem to solve. So we said it therefore means that you can use your computing software. First, you construct a vector y of your output data, and then you use your input data now to construct phi. And then afterwards, you calculate the Moore-Penrose inverse, which is this one. So you calculate this inverse, and this is done in Octave. You will see that the transpose in Octave is simply a dash. The T here in Octave is that. So you take that inverse and then you multiply it by y. And then this gives you two values. It gives you a vector with two values. This becomes your theta. And the top one becomes theta 0. The bottom one becomes theta 1. So therefore means that your theta 1 would be approximately 0.51, which is that. And theta 2 is approximately 0.79. So at this point in time, we have covered all of the lectures containing or pertaining to modeling of systems, which is supposed to be in unit 1 of the lecture lecture notes. So we have looked at the introduction to control systems. We have looked at examples of designs of control systems and what the control system procedure contains. Now, if you want to further read the theory related to these topics, you are free to go to the reference book sections 1.1, 1.3, 1.4, 1.5, and 1.9. We have also looked at this point, reviewed the use of differential equation. We have reviewed the application of transfer function models. We have looked at new information, which is how to do linear approximation of nonlinear systems. We have reviewed RLC circuits, fluid flow systems, pendulum, and thermal systems. We have just looked at system identification. If you want to review this information, you are free then to go to the book sections 2.1, 2.2, 2.3, 2.5, and 2.8. We have also recently looked at how you can use what is state variable representation and how it works. We have looked at the state variables. We have looked at state variable differential equation. We have looked at how you can convert transfer functions to the state equations and the other way around. If you want more information on this, go ahead and read sections 3.1, 3.2, 3.3, as well as 3.6 and 3.9 of the reference material. This should be enough. This together with practicing the tutorial should be enough to get you ready for assessment